So what are our general updates? I appreciate to see that you keep sending me homeworks. Already several people sent homework number 5, which is due today. And please, the more you send me, the better, because then the earlier I will post it. I will post the solution and you will need it for your final exam. So also please send me whatever you owe me still. So many of you still did not write two paper reviews. One is on my paper, one is an arbitrary paper on combustion. Again, you can do it before the final exam anytime, but again, I do believe that at your final exam you have many other things to do. So I would recommend you. So please, you can do it earlier. Send it to me. Now, what else? I will send you, and again, two things I will send you. And typically, if you were in a class today, I would give you another quiz, but now to save time, I want to give you like take-home quiz, or let's call it homework number 6. It will be just set of questions, theoretical questions, multiple choice questions. So what I will be doing right after we end the lecture, I will send it to you. And please fill it out. And you can, again, it will be Word file, so you can type in it and send it to me. You can print out, write down and scan and send it to me, whatever I want. And you better do it by tomorrow or tonight. Again, it will not take time if you know the topic. If you don't know the topic, it will mean that you need to go through my slides, my notes, all the style, which is good habit, good practice to do. So please do it such that by Thursday I can post it as well. And again, I did not bother you with this earlier because I wanted you to complete homework number 5, but now send it both of them and I will post it so such that all homeworks will be posted. It's important to have it posted such that you do have the solution. It will be there. And now, also I will send you topical overview for your exam, such that, again, you know how my topical overview works out. So please make sure that when you read it, it will be like 36 topics there altogether. Please make sure that you have something to say about each of them. If you have nothing to say about any lines there, it means that you don't know this topic, so please learn. Now, your final exam. So your final exam is formally scheduled on next, let me just one more time double check. And basically now the associate dean sent us the schedule. So your exam is on Wednesday, May 6th and basically I will start showing my screen now. And I think it's time to do it. Yes, please. I will show the screen. So your exam is on Wednesday, May 6th, starting at 8 o'clock in the morning. But I know that this time it takes more effort because it may be internet problem. You need to open your notes and it's the open notes exam anyway. So what I will be doing, and I will send you text of exam like we typically have with empty spaces. What you can do, you can print it out if you have printer to write it on it. Or you can type your answers in the Word file. Or what you can do, just take set of piece of papers and just write it down on it and scan and send it to me, whatever you want. And I don't want to be addicted with the time because I know some of my colleagues do take home exam and give you any time to do it. So what I intend to do, and I believe the dean's office will allow me to do it, I want to have exam during the entire day of Wednesday. So at 8 o'clock it will be posted and sent to you. And maybe I will arrange Zoom meeting if it's still open to interact with you, but you can send it to me by the end of Wednesday, by midnight. Why I want to have it by mid, and please, if ever possible, please send me everything you owe me by the end of Wednesday night, because I do want you to complete this class and to put your final grade by Wednesday night. And on Thursday I will have the same exam for my turbulence class who attended, so I want at least to split it. Again, potentially we can do something after this time, but I think it's a good time to get rid of it. And also, please evaluate this course as you usually do. We still have this policy, we still have this practice. I still want to go for promotion next year, so we need all the evaluations. Now, any question about our reglement? So, what are we going to do now? 2 lectures left, actually, today and Thursday. And yeah, if you look at the schedule, formally you may see that we have 3 portions of slides, 3 lectures left, number 13, number 14, and number 15. But believe it's not we are behind the schedule. Every year it happens like this because last 3 lectures are really extended, so I will give you only piece of the materials. And you may remember that I did not send you PowerPoint slides yet for these 3 lectures because it will depend how we go. So lecture 13 that I'm going to talk today, it is about applications to mining safety. And believe me, if you were on site on campus with a class, what would happen typically today is that I would bring one of my students who really work on mining safety, and he or she will explain exactly how we employ this theory to practical mines. Now I will do it myself, but again, it will be extension of what we used to do. And basically, you will know now that how we can employ our theoretical predictions. And again, I will also post my video on it. Lecture 14 will be quite fragmentary. I will give you maybe introduction about triple flame, what it is. It will be tonight. Otherwise, I'll post a lecture maybe beginning of Thursday. And also what I really want to do on Thursday, I want to give you a lecture on extension of combustion science to other fields like supernova, like material science, like laser ablation, controlled fusion, and all those things. It's really something challenging, something interesting, and that is I always end my class with this. Also, I keep posting lectures that I think I told you that one of records was lost, so I re-recorded it. So now all lectures 7, 8, 9, 10, 11, 12, they are all on eCampus and on YouTube. You may take it, and eventually I will provide you with latest links of all of them. They're all there. Well, some of them are by parts. So for turbulence, we have 2 sections. For controlling scenarios of DDT, we have 2 sections. And also, I do want, and I am going to, before your exam, to post other lectures. So what I already did, I prepared at least a piece of lecture 7 when we talk about planar flames. I also want to have some kind of lecture 5. Well, I don't think we really need big lectures of 1, 2, and 3 because mostly it's like overview. But when we start talking about equivalence ratio, about chemistry, about thermodynamics, we better have it. So that's I'm going to post. Okay, well, that it is. So what we will do now? Let me please let me open my screen now, and this will be lecture 13. So coal mining fire safety. And now I should tell you something. So believe me that many people who work with coal mines, they don't work with combustion. They work with, even people who work with safety of mines, they work with things that happens with health condition, with safety issues, with some kind of risk assessment, but it's not necessarily combustion. And I should tell you that I'm not expert in combustion. I'm not in mining safety department, and I knew very little about mines. And when I came to West Virginia, when I came to WVU, when I got my faculty position 8 years ago, what I started doing, I did not consider me like any kind, not even expert, but anybody, like a person who may work with coal mines. I was just a researcher who deals with engineering, with combustion science. And my point was to employ what I know about combustion, about flame propagation to various aspects to apply to, and I was, what I started doing, I applied to different agencies to try to get some funding. And well, and I understood the time that since I talk about flame acceleration, since I deal with flame acceleration, there are 2 directions in which I can proceed. It can be promotion of flame acceleration for better efficiency, and it can be how to prevent it. That is fire safety issues. And that's helped me to establish cooperation with Worcester Polytechnic Institute and work on fire safety. But you know what? It's West Virginia, which is traditionally strong in mines, and in coal mines especially. Now we talk about shale gas, gasification, we talk about oil, but traditionally it was strong in coal mining, and WVU is traditionally strong in this. And when I started applying for funding, the first money that I received, it was seed money from the university, it was on coal mining. And the second grant I received, it was on coal mining safety. And the third one, it was also on this. So at some point, it looks like I become in this field. And when I got this funding, I started to think, so what we can do, how we can employ what we know about combustion to coal mines. So where there is a match between coal mines and what we are doing. And that's what I want to talk today in very basics. So basically, you know what? And very often when I talk, when I show, when I start the lectures, I should say that why we talk about coal mines? Why about fire safety? Because coal mines, it's one of the most, if you work with in mine, it's dangerous. So this industry, coal mining industry, historically has one of the highest fatality and injury rates. Even now, it's much more safer than a century ago, but even now, every year people die in coal mines. If not in the United States, in other countries. And well, they don't die definitely because of explosions, but because of something that happened inside the mine. And this really key point. And in West Virginia, it was catastrophe in Upper Branch Mine in 2010, and about 30 people died there. And that was inspired to organize Alpha Foundation, which really supports coal mining study. And one of the directions in this study is how to prevent explosion. Because what is the one of the major disasters in happening coal mines? You may know that when people excavate coal, there is dust, right? There is coal dust there. And also, combustibles don't stay there separately. So when you deal with coal, there is some combustible gas and combustible liquid sometimes. So basically, what is typical combustible gas you have? It's methane. So in fact, oftentimes there is methane in coal mines. And you may know that what is typical disaster that may happen, it's methane explosion, right? Sporadic methane explosion. That's what happens. So people try to avoid it. People try to avoid methane. And if concentration of methane is quite high, what people try to do, people really try to mitigate it, to vent, to get rid of it. And well, how people measure methane now? Now people have indicators that they show it. But you may know that a century ago what people did, many actually miners, they have birds, like canary birds, some kind of other birds, or cats. Sometimes they use like animals, like cats, like mice, but typically they use birds. And they took these birds in a coal mine. Why? Because birds are very sensitive towards their breath. And when these birds or small animals start like dying or has problems with breathing, then coal miners realize, okay, something goes wrong. Maybe it's some kind of dangerous gas here. We should go out. Well, it's not too risky. Okay, then you say that, okay, so now you have some kind of indicators that what we are doing. The problem is that it's not methane itself which is most dangerous. People can measure it. But what typically happens is that there is dust. And there is coal dust. When you excavate coal, especially when you use modern devices, there is like really refining dust. And dust interacts with methane. So you don't have just methane, you have just mixture of methane with combustible dust. And this is very, very explosive because concentration of energy in dust is extremely strong. So that's what may happen. You have methane air dust explosion, which can go into detonation. Now, so what people do? So what a typical strategy how to avoid it? So first of all, there are actually 4 stages what people can do in mines. People say that one strategy is the following. First of all, we want to predict the risk of particulate coal mine fire. So we want to say that may you have explosion or not. So people start putting indicators and measuring what is the risk of it. And what is the problem here that you cannot measure uniform concentration of methane. So oftentimes concentration is quite small, quite minor. But you may have in one locus increased concentration of methane because of some kind of ventilation, because of some kind of mixing. And if it interacts with dust, that's how explosion may happen. So first part, what people try to do, people try to avoid a risk of explosion. People want to avoid it at all. And here, I frankly speaking, I cannot help much. I'm not working on it. By the way, there are many teams, even in WVU, people who deal with these measurements about new generation control devices. And for instance, maybe Dr. Derek Johnson in our department, he really works on it. He has funding from Alpha Foundation. He works on this indicator. Now, imagine that it did not help. So imagine that by some reason, and some very unfortunate reason, still something happens. Still some kind of source of fire started. So what we want to do? Right? We want to kill the fire. We want to suppress the fire. We want to suppress the flame. We want it to extinguish. Right? So we want to have a strategy how to suppress it. Okay. This is second level of security. Third level of security. Imagine you cannot suppress it. So what you want to do? You want at least to mitigate its propagation, right? So you want to run away from it, because remember that slow flame, if it was planar slow flame, it propagates like slowly. It propagates like a couple of meters per second, so you can run away from it. So you want miners to run away or at least hide themselves. So our strategy would be what? To prevent flame acceleration. And the worst scenario, latest level of security, number 4, if you cannot prevent flame acceleration, if it still accelerates, you want to prevent or mitigate or postpone transition to detonation. Why? Why detonation? Yeah, you may say, of course, detonation is very dangerous. You don't want to be fired by detonation because it's very fast. You know what? Detonation has one more problem beyond combustion. Because what is detonation? It's a shock wave. And shock wave propagate in enclosures like coal mine, like a tunnel. It propagates very, very fast and on very long distances. You may know that what happened if there are some terroristic attacks, when they are most dangerous, if it happened in subway somewhere, because this shock wave goes really far away on long distance. If you have explosion in open space on the ground, well, like any wave, it expands. So when it expands, you have divergence and wave cannot be very strong. But when it goes in subway, it can propagate on kilometers and still keep affecting people. And it can crush equipment, and of course it can wander and kill people. And you may realize that pressure abundance, pressure jump, pressure rise is very serious concern. Because you may know from thermodynamics class, from other classes, so that in fact we all have atmospheric pressure in our body, and so it's balanced. But pressure rise, it's really something strong, something really big difference. If you have pressure rise of about 10% of atmosphere, 0.1 bar, pressure abundance, pressurized, this pressure is enough to really crash windows, destroy some kind of equipment, and it can, if not kill people, but really wander a lot, it can actually destroy some kind of really internal organs. While pressure rise up to like 1 bar, comparable to 1 atmosphere, it can really kill people, it can really crush even structures. So that's something serious. So, and when you look at this picture, why I show this? So what we see here, we have some kind of coal mine tunnel, right? And does it resemble you something? Remember, we spent a couple of lectures on flame acceleration and DDT, and before we talk about finger flame scenario. Why did we talk about finger flame scenario? Because finger flame, remember, it's Reynolds independent in scale invariant. So when I describe flame propagation, it can be nanotube, it can be microcombustor, but it can also be tunnel like this coal mine. And that's what we are going to discuss. So basically, imagine you have coal mine, you have long tunnel, and you have explosion. You have sudden explosion somewhere at the center of the corner. So let us describe very basically, very qualitatively, what will be the stage of fire propagation, how it will go. So what happened first? And here you may see on this picture how it goes. So what happened first? First you have ignition, you have micro explosion, and then your flame, your premixed flame in your air dust environment will propagate, will expand. Right? So first remember, if it will expand like spherically with smooth front. But what happened next? Next, there are two things that may happen. One thing, remember finger flame acceleration that we discussed, that when you start approaching to the wall, it will be like this. But also, in fact, coal mines, it's a big domain. It's actually 2 meters of diameter. So the real and down instability may and will develop in this configuration. Here it is. So the real and down instability will develop. So instead of smooth flame, you will have cellular flame structure and flame will accelerate. Later, you will have this kind of 2 finger flames that will propagate faster to the walls. After this, what will happen? After this, it will be wall friction scenario. But you know, remember that wall friction scenario, it's not very important because here we have big Reynolds number. So most likely now in mine it will not be. But if you have obstacles, and we typically do have some kind of obstacles in a coal mine, like boundary hidden doors, some kind of pillars or whatever, then they will provide acceleration. Of course, it's not, well, you may say, why do I say obstacles like this? Definitely in coal mines, you don't have regular obstacles. We will talk about worst scenario, okay? Worst scenario of acceleration. It will be worst scenario. So if you have better condition, okay, you don't need to investigate. So basically that's what we want to see. And we will develop a theory of flame propagation in coal mine. And here we will employ what we know. Expanding flame theory, finger flame theory, and obstacles-based flame acceleration. Do we know all of them? Yes, we do. Remember, this is chapter 10. This is chapter 11 and 12 together, right? Actually, chapter 12. So that's what we are going to do. So basically, we will consider expanding and finger flame acceleration scenarios, and we will develop it. And also, I will show we have a computational platform that allows to consider how flame propagates. So, finger flame, and again, what I will show you here, if you really are very good students, you may remember it from previous lectures. It will be nothing new here, but it will be new how you can combine it. So remember finger flame scenario? Remember how it goes. Finger flame, here you may see a movie, how finger flame goes and from the axis, and that's what you have. You have a channel, you ignite your finger, and it goes. I don't know what happened with me here. Let me show it here. Yeah. This mode. I don't know why it's like this. Okay. Yeah, it goes. Because initial stage of propagation is quite long. And here you may, on my screen it goes. And here you might see all the scenario, how flame shape appears. It goes, it accelerates until the flame skirt touches the wall, but then acceleration stops. And what is important here, you may see two things. One thing, that you will have the same scenario in micropipe and in coal mine. You will have the same flame acceleration with the following exponential acceleration. So what is our analytical model? What we can do? Here we combine expanding flame theory. Remember expanding flame theory? Remember this formula for the real and down instability, how flame accelerates, and finger flame acceleration. How we combine it? Again, of course, rigorously you should simulate it directly, which is difficult, but we do something simple because you may realize that when I talk about coal mine, when I talk about big flame surface, I mostly should not care what happened on small scales. So basically what I will consider finger flame acceleration. But instead of planar flame parameters, instead of what we call SL for finger flame acceleration, Now we will have the real and dow parameters. So instead of planar flame velocity, I will have the real and dow velocity, which depends on the characteristic size, which depends on the real and dow cutoff scale. Everybody remember this? Again, I don't request you to rederive these formulas. If you did homework number 5, you should be flexible with this. But I want you to realize that what we are doing, we take finger flame acceleration theory, but now instead of a cell, I will have time-dependent the real and dow term, which shows much faster acceleration. And if you do it, that's what we see. That is your finger flame theory. And you may see that first you have hemispherical frame expansion, then your flame will become elongated, and then it will touch the wall. And here you may see characteristic timing, characteristic equations, a characteristic timing at which flame will become, will have transition from spherical to finger shape, and at which time it will touch the wall. Here they are. Just timing, and you may see this time versus equivalence ratio. And here we can see the methane, also propane. You may ask me, why do we talk about propane? For 2 reasons. For 3 reasons, actually. One, you know, I am physicist rather than engineer. I always, when I investigate methane propagation, I want to have some other fuel to compare, to have comparisons to see. Because propane is much more explosive, we want to see how it goes. Second, you know, we don't talk about coal mines only. Very often in subways, in other setups, we may have propane explosion. For instance, now we talk about propane is classical cooking gas that people use. And if you talk about future subways where it can be tunnel, which you have car filled with fuel tank, it can be eventually propane explosion. Plus in coal mines, very often people use some kind of devices that may contain propane. So, but simply, of course, in reality, we talk about methane. Well, another point here is the following, that if we talk about fire safety, oftentimes we employ shale gas utilization. And shale gas is oftentimes simulated by methane. But on the other hand, it contains various fractions which can be important, and propane-like fractions can be here. So that it is. And you may see how characteristic timing, and you may see that if we have stoichiometric combustion, remember phi is equivalence ratio, when it is unity, definitely you have fastest propagation. And when you have lean or rich substance, it goes slower. And you may realize that definitely in coal mine we are lucky we would not have stoichiometric combustion because we want to avoid it. We will have quite lean combustion, but still it's something. And yeah, and in this chapter, we will talk about dimensional units. So you may see timing here. So what is the characteristic time when flame will touch the wall in seconds? It's about 0.7 seconds. It's quite fast. You will not get rid of it. So here you may see characteristic flame propagation characteristic with versus here upstairs. You can see the stoichiometric combustion, and you may see how flame tip velocity, flame tip acceleration, and flame tip position change with time. Here is acceleration stage from T spherical to T wall. This is when flame start propagating and did not touch the wall yet. So you may see this acceleration. It's quite big, so your velocity can attain 600-700 meters per second. I want to also point out flame tip position. So basically it will go very fast. This is our timing. So in 0.1 second, in 100 milliseconds, flame will penetrate through 8 meters. So it's quite big, quite fast. So people cannot run away from it, but some robots, some devices, they can turn on alarm, they can do it. And even some person who will not survive in this catastrophe may put some button on the alarm, because typically why also this timing are important? Because what is the smallest time that you resolve? What is correct? Because like when we talk, we count by seconds, right? But what is the smallest time that your ear resolves? Well, it depends on people, of course, but you know the effect of cinema of 25th frame. Because if you almost see any movie, typically you have 25 frames, at least you should have at least 24 frames per second. Then you don't see how they're changing. It means that your typical resolution time of your brain, of your eye, of your ears, it's about 50 milliseconds, something like this, 0.120th of a second. So with this time, it means that you cannot run away from it, but you can somehow react. You can report. You can alarm it if required. And it's important to deal with this characteristic timings. So that is flame, how it propagates, that is the velocity. And you may see that these velocities are really big, it can attain detonation stage. And here, what you have here, it's acceleration. Well, what's acceleration like? Second derivative of replacement. And I want you to show something. Well, in principle, this acceleration is nothing, but it's not like some physical quantity, but I want to show the value, it's my thousand. So basically you may see that this acceleration exceeds gravity acceleration. So really, the shock wave which form we make can kill people. And what if you see pictures on the bottom, it's even more interesting. Picture on the bottom shows how flame tip position, velocity and acceleration, maximal flame tip position, how they, which attain due to finger flame acceleration, how they change with equivalence ratio of V. And you may see that yes, if you have stoichiometric combustion, your maximum velocity will be detonative, it will be 700 meters. But if you have quite lean combustion, you don't have very lean and very rich because it will extinguish. But if you are here and here, what would it mean? It will be something right about 150 meters per second. So it's comparable to something that you can, if not run away, to at least get high. So one of the key parameters of combustion is what people call run-up time and run-up distance. What is run-up distance? It's what is it? So it's how long does it take for a flame, distance and time to detonate. So we start with a flame, it accelerates, and eventually detonation will happen. Estimations that we make here are quite raw, and because it's by order of magnitude, but it's okay because when you want to survive, it's okay to see how much time you have, seconds or milliseconds or microseconds. So what you say typically, because how we estimate here? We know the following, that detonation is supersonic, right? Deflagration is subsonic. So by order of magnitude, when do you have switch from flame to detonation? When the velocity becomes by order of magnitude sonic velocity. So that is we do. We know how flame goes. When flame tip velocity becomes sonic, it means that it may detonate. And this allows you to find characteristic timing from here and characteristic velocity. And what you will see here, this is for two-dimensional. And if you talk about series, we consider two-dimensional and cylindrical configuration. You may ask me, so why do you say, what is cylindrical? Actually, and Dr. Derek Johnson actually once upon a time asked me, when do you see cylindrical coal mine? My answer is the following. I do saw cylindrical subwave, so, and in subwave it propagates like this. Regarding 2D, well, 2D is simplification, but really what typically we may have rectangular or square cross section, which resembles this one. So we have all these theories that how it goes, and you may see how flame run-up distance, so detonation distance at which detonation happens, how it depends on phi. So what you may see here, this color plot shows these values for methane is shown by this dashed blue line, propane is shown by brown line, and this is in cylindrical configuration. And you may see that definitely methane is better than propane, it's less explosive, but still it's not too good, because if you have stoichiometric, and also what is nice to see here, you see that when you have like minimal values, when you have fast, what does it mean that run-up distance is minimal? It means that you have fastest combustion. So when you see fastest combustion, you see it's not when you have U1, it's a little bit shifted here. And you know why? Because remember about right shift, that in fact not all combustion is completed. So remember that your maximal velocity corresponds not to stoichiometric case, but a little bit higher. Remember chapter 4, lecture 4 from our class. So here you will have minimal run-up distance. So basically here it is, and you may see that run-up distance are quite big. For stoichiometric conditions, that will about 4 or 5 meters. So it's very fast. Flame will propagate 4 and 5 meters, couple of several like 100 millisecond maybe, 50 millisecond, and then you have detonation. But if you have clean combustion, most likely in reality we are here, it's not bad. So here this may propagate up to 50 meters, something like that. Now, this plot, black plot, corresponds to this 2D configuration, and it's only for propane. Why? Because for methane, we don't expect the detonation due to finger flame scenario. So we are lucky. It looks like when the flame will touch the wall and slow down, detonation will not stop. And that's excellent, because I tell you, detonation itself is it's really very dangerous. Because what also happens? What people do in coal mines? People try to hide, because very often you understand that you cannot run away from it. So very often in coal mines, you have some kind of storages, some kind of closed rooms, some kind of places in the wall that miners can jump in and stay there. And the idea is good, that you can jump in and stay there, and if it's just a flame, no detonation, you will not be killed. The problem is that, what does it mean that you have storages? Imagine configuration, you have a big channel and you have storages. Does it resemble you something? It should. It should resemble you obstacles base toothbrush configuration. And you will see that, in fact, having these places, these shelters, how to say, it's not safe, because flame will accelerate fast. You may stay there, but flame will come to you much faster than otherwise. So here is, please remember, run-up distance, it's a key parameters for safety issues. So that's what we have. Now, another point, what we may count is, we have also, in fact, what we show here, in reality, we are more lucky than you may see here. Because remember, when flame accelerates, it slows down. We discussed it. And eventually it saturates to some steady regime. So in fact, here are equations that we can use. We have isentropic approach for density, pressure, and temperature. We extended. Again, my task here is not to teach you how to solve these equations and how we will ask you to reproduce them. Idea is to teach you what you potentially can do in combustion research, right? This is fundamental of combustion course, and after your graduation from this course, when you all pass it, you should be able to know what book to open and what research direction exists. So basically, this allows you to account for compressibility, and we come to the final equation which describes propagation with account for compressibility in rectangular, let's say, two-dimensional configuration, and in cylindrical axisymmetric configuration. Here it is. And if you solve this equation, that it is. So you may see here on this picture that it's really important to account for compressibility. So we are on the safe side. And I told you, now I talk about finger flames only. I don't talk about obstacles yet, because obstacles, wall friction, used to be considered as small ones. So here you may see the picture on the top, actually, by the way, it's logarithmic scale. Here shows time change in seconds. So it's 1/32, 1/16, 1/8, 1/4. So dashed lines shows finger flame exponential acceleration, how it would be if it was just incompressible. And solid lines shows corrections due to compressibility. So in fact, it is solid lines which are realistic. This is real the case. Okay, does it make sense? These solid lines are realistic and real the cases. Here it is. So, and you may see that, and a picture on the top shows flame tip position in meters, how it propagates its replacement, and its derivative, its velocity, flame tip velocity is here on the bottom in meters per second. So you may see that its velocity is quite big. So of course, fastest acceleration, fastest propagation you will have for stoichiometric condition. And here we see what we have if you have lean or rich combustion. Well, rich combustion does not make big sense for mines, for methane explosions, but lean one is really something important. So that's your velocities, which they are. And you may see that even you don't take detonation, your velocity is quite big. So let's see what is the velocity that you can attain. It can be 50 meters per second for stoichiometric case, and here it's about, yeah, about 50, 100 meters per second. But if you have lean case, it's about 10 meters. You know, so from this one, you can run away. If you run very fast, you can run away pronto and you will not attain it. So your strategy to mitigate this scenario may work. For cylindrical, here is the same for cylindrical configuration. So you may see how it goes. This is, again, this is flame tip position and velocity. Values are larger. You may see this is case when you count for compressibility. And again, you may see that if you have lean combustion, your acceleration is slower, so there is no big effect of compressibility. Why there is no big effect of compressibility? Because your velocities here are really strongly subsonic. But when you come closer to detonation, to fast velocities, compressibility come to play and slow down the effect. So it's nice. In fact, what happens, so if you have slow combustion, maybe exponential acceleration theory is okay. But when you have fast scenario, you should not account for exponential acceleration. You really should account for compressibility. Please consider this. No, so sorry for these frames. I don't know what all this commercial appeared. Some girls appears here, what they want. Luckily, my wife does not take my class, so she does not see my screen. Okay, I don't know why it happens. Sorry for this. Okay, but I see you see my screen with mining safety issues. Okay, so now, next portion is most important. So I told you that why we talk about coal mines if I talk about methane explosion, because there is dust in coal mines. It is dust mixture with coal that gives you something. Now, how to, so if in fact what we have, even if you have premixed combustion, you have a mixture of what? What are premixture? You'll have mixture of methane and dust. Dust is solid. These are like dust particles, they call dust particles. Their typical size is quite small, with some kind of micro, so like 7 from 10 from 10 to 100 microns. Then they're quite small, so you just hardly see. While here, you will so what you will have? You will have gaseous combustion with these kind of particles. And how to deal with it? How to investigate it? So of course the correct answer would be, okay guys, you should do simulations or some kind of measurements of multi-phase flow. So if you want to do serious study, you should consider multi-phase simulations. But we are lucky that we can do something easier. There is so-called Shadri formulation, which allows you to incorporate solid particles, dust particles into our consideration. So what we do? So you realize, in fact, that there is no many dust particles in methane. So your dust particles by volumetric, the fraction, volumetric fraction, typically it's 120, 100, 120 gram per meter cube. So volumetric fraction does not exceed maybe 1%, even 1 promille. Mass fraction is larger because it's solid, but it means that you are lucky. There is a way how you can describe it. So instead of considering multi-phase flow, multi-phase fluid, we do some simplifications. It's lazy but sophisticated. So we consider, let's say like this, instead of considering methane combination with coal dust, we will do the following. We will consider effective fluid. I will say I have effective methane, effective fluid. So I will replace my gas particles by some effective fluid. But in this effective new fluid, transport properties will depend on dust. And now that is the Shadri formulation, that's how we can incorporate. So instead of planar flame speed in this new system, I will have dust-induced flame speed. Does it make sense? And it will exactly play the role of planar flame speed. You may ask, how can you do it? Why? Because I remember, and by the way, very often people ask, okay, why do we talk about gas, and fluid, about fluid mechanics? Because when you take cigarette or when you burn wood, any kind of wood stick, then it looks like it's solid. Remember what actually happens. Your solid combustible item is first get preheated, then it melts. We have volatilization and you have melting. It becomes gaseous. It evaporates. And when it becomes gaseous, combustion happens. So combustion happens at gaseous phase. So in fact, when your solid particles, coal solid particles will melt, they will become methane-like. So in this configuration, we consider modification of equivalence ratio. So you'll have extra new equivalence ratio, extra new methane sources. Again, I don't want you to dive deeply in how people do it, but the idea is the following: that you incorporate dust particles and deal with it. and now you will have effective fluid with modified transport properties, modified viscosity, modified heat transport, modified planar flame speed, and you can investigate. One more important thing. In addition to cold particles, you have in coal mines, luckily, you always have what? You have inert particles. You have rock, right? You have sand. And basically what you know what firefighters do when they have fire? They put water or sand to kill it, right? Why? Because it's opposite situation. So gaseous combustible particles evaporate and produce extra fuel, but sand particles, they eat heat, they take heat from evaporation, they take combustible heat from your methane, but they don't burn. They don't burn its inert particles. So basically, what we can do here, we can account not only gaseous particles, but also not only combustible particles, not only coal, but sand as well. So that's what we do. And basically this allows to extend our formulation. What will happen? So basically here it will be our new modified equation. And you will see what we count here. We account for modified equivalence ratio. And here we count for so-called heat sink effect. It will mean that your particles will get heat from combustion, which moderates the fire. But on the other hand, after this, it will become extra, it will promote equivalence ratio, it becomes extra source of fuel. And we realize it is dust particles which actually give you promotion, which actually give you why fire happens. Again, Sichardi formulation of this is purely theoretical work. It was 1992. Dr. Sichardi, he is professor in University of California, Santa Barbara, if I'm not mistaken, San Diego, I'm sorry. And he works on fire safety there, but it's not for coal mines. He just developed how planar flame speed depends on solid impurities. Here, what we managed to do, we incorporate these formulations to consider effective fluid. So basically, here you may see what we can do, combined effect of promotion and prevention of acceleration. And well, and here are modified versions of what we see before. So remember, let me go here back. So here was how flame propagates, This is flame tip position, that is flame tip velocity for compressibility, how it changes with time. Now I will show you the pictures, how they look like when you incorporate for particles. Again, so dashed line will show exponential acceleration, solid line will show the effect of compressibility. And again, you may see that when you have slow acceleration far from detonation, it's okay to employ incompressible formulation. But when you come closer to it, you should consider incompressible. So here it is. And so what you will see here we incorporate different scenarios. Here we incorporate cold particles, and this is flame tip positions. This is on the right hand side, you have cylindrical configurations. Here you have rectangular configuration. Here time dependent. So this plot corresponds to cold particles of size 10 microns. And this one corresponds to 75 microns, and this corresponds to no particles. So you may see that big particles, in all the cases of what we see, we can see the equivalence ratio 0.7. You may ask why it's so big, but in fact, here we already account for the effect of particles. It's already promoted equivalence ratio. And if you took equivalence ratio like 0.5, it will mean that without particles, it will be too small and there will be no combustion. And another point, it's concentration. Here we take 120 gram per meter cube. It's typical concentration that it happens in this condition. Again, two particle size are considered, 10 microns, 75 microns. So, and basically, if you remember, a week ago, I delayed my lecture for a long time because it was defense of my student Furkan. So he works on mining safety, and one of the questions he got, what are these magic numbers? Why people have 75 micron, 10 micron, or why this concentration? I did not have like answer on this, but what I understand from fire safety people from Worcester Polytechnic Institute, actually, if particle, that is a particle that plays a role. So if your particle is less than 10 micrometer, particle is less than 10 micrometer, it means that this particle will be not seen by flame. It will be really less than flame thickness and you can neglect it. If particle go from 10 to 75 micrometer, it really something that it modifies transport properties and modifies the flame. Larger particles either happen seldom or they should be considered like bluff body, like solid body. They are too big to be incorporated in consideration. And this is a typical concentration at which explosion happens. If concentration is less than this, you are fire free, you're safe. So these are the values. Again, I tell you, I'm not expert in coal mines at all. So here it is. Here are the values. Here is how it goes, with and without particles. And here, flame tip velocity, and here it is. So, and what you may see here is that small particles play larger roles in big particles, because what happens with the same concentration? If you have smaller particles, there will be just more particles to participate, right? And that it is. And basically, but what are our parameters is concentration and particle size. So here a picture shows what happens. This is the maximal velocity and maximal flame position that can be attained when flame touches the wall. And here it's versus concentration. I tell you that 120 gram per meter cube is typical concentration, but here you may see how these values depend on the concentration. And this picture on the left shows combustible particles. Yeah, actually, and yeah, picture on the top. Here we have combustible particles, and here we have combustible particles. And while here you have inert particles, and that's understandable. So what inert particles means? If you increase the concentration of inert particles, actually you will slow down the flame velocity. Correct? But flame position will still go. And now it's something curious. So if somebody wants to bonus ticket, please explain me, for instance, why here I have declined line for your tip, but here increased line. So like before we see here, tip position and tip velocity, they are quite collinear, right? Because this is derivative of this one. Why here you have monotonic increase for tip position, but monotonic decrease of the velocity? And here it's vice versa. What do you think? Why the trends are opposite? Please think about this for a couple of minutes. Maybe not a couple of minutes, because we should end the lecture in 15 minutes, but a minute. Does anyone have idea about this? Well, the answer is quite simple, because in fact we talk here about maximal velocity and maximal position when flame attains the wall. So it's not this one on the right, it's not derivative of left hand side. Because what happened? Flame propagates and touches the wall. So the faster the flame velocity, the later, sooner it will touch the wall. So its propagation will go lower time. So basically what we have here, if your tip velocity is lower, it will touch the wall later, so the tip will be larger. It's very simple. The slower you go, the longer you will survive. But key point here, you may realize the effects. So definitely inert particles, they kill flame, they slow down the process, combustible particles promote it. And here you may see the effect of the concentration. And the effect is the following, generally speaking, that in fact, particle size is more important than particle concentration. Does it make sense? Any questions about this? So this is basic idea of what we employed. I don't talk about obstacles here, how it incorporate, but the idea is the following, that we combine the series we have, and this shows you example, what we actually can do, what we can potentially do to incorporate particles, to deal with this, and how it works. We started with gaseous combustion, then we incorporated particles. And we combined theory of expanding flames, this is chapter 10, and added finger flames, chapter 11, and we described it. Another things I can show you is we also have our solvers. So if you want to simulate coal mines, again, we can do exactly the same story that we did before, because we managed to incorporate coal particles into the solver. Again, we incorporate Seshadri formulation. So here is our, for instance, if you talk about simulations, here is our classical platform that we use You may know that it's continuity, Navier-Stokes equation, energy species. And what we did, we employ C# reformulations to deal with it. Again, it doesn't mean that you should use our solver, but that's the way how you incorporate. So now, instead of using multi-phase simulations like people use ANSYS Fluent or other, or Star CCM or other mixed solvers, potentially you can incorporate C# reformulation and deal with effective combustion. And what we also investigated, it was an interesting point, because very often people say, okay, so what is real dust distribution in coal mines? And that's what we investigated. Because if you have different distribution, it can promote and slow down the flame acceleration. Because for instance, if you have finger flame, and in finger flame, you know that flame tip propagates in the fastest manner, while flame skirt propagates in a slower manner. So, but you may realize that if flame tip goes through dust, while flame skirt does not, you may elongate or compress the flame. So what we investigated, and at this point, so what we considered, we considered different kind of scenarios. We considered different dust distribution, dust concentration distribution inside the channel, inside the coal mine, and see how it will promote or prevent the flame. Okay, here you can ask me, okay, so what is the real distribution in coal mines? And my answer is, I don't know. And for a couple of years, nobody actually can give me real distribution, how they mean it. But again, in these studies, it's always nice to be pioneers, because when you can deal with spherical horse in a vacuum and get some result. And later you will update it when you have something more realistic. So what we consider here, we consider uniform distribution of coal and some kind of polynomial or hyperbolic or Fourier distributions like hyperbolic, parabolic, and cosine distribution. And basically that's what we see. We made simulations how flame goes with time in the case of homogeneous distribution of dust, in the case of linear, parabolic, cubic, in the case of no dust. And that is how flame velocity change, this is how surface change. We did it for, and what happens, we did it for, remember pictures like we saw previously in previous lecture. That was for finger flame acceleration and for wall friction effect. Here we do the same, but now we incorporated these various dust particles. And you may see these strange features why it happens, because now you have different dust distribution, homogeneous, linear, cubic, parabolic. This is exactly what you saw in lecture 12. And that is how it will be when you non-uniformly modify the dependence. And our result, and actually you may see, I hope movies will show, that's how it happens. That's how homogeneous goes. It's uniform. That's how linear goes. When you have linear distribution, you see it gets elongated and propagate. That's how cubic distribution behaves. And that's how parabolic distribution. Well, you may see that definitely parabolic and hyperbolic are symmetric, while cubic and linear are non-symmetric. So basically what our conclusion was here, I can tell you, that, well, was it my last slide? Yes, it was last. So basically, preliminary conclusion from here was that we are lucky that any kind of distribution provides slower flame accelerations than uniform. And you cannot have uniform distribution in coal mines. And this gives you another strategy how to deal with this, how to avoid, how to kill the flame. Because all distributions will actually suppress flame elongation, suppress geometrical effect. Okay, that was chapter 13. Annie, please ask me questions. Please ask me questions. May I believe that everybody understood everything? Well, there is one more chapter, chapter 14. I will not go through all this chapter today, and actually I will really limit consideration here. But the key points that I want you to discuss here, that so far what we deal with, we talk about, I just want you to give basic hints. What we may investigate, what we deal. So far we deal with what? We talk about diffusion flames and premix flames, and most of the course was about premix flames. And I mentioned a little bit that sometimes we deal with partially premix flame. So what I want you to realize, and actually what I will talk, that sometimes we have combination of these flames. Typical scenario happens if you have picture like this, you may see on my screen. So basically that is so-called triple or tribracial flame. So basically features like this. Imagine you have a nozzle. Imagine you have a nozzle as there is a flow from the nozzle. I think I should show configuration, yeah, like this. So basically, imagine you have some kind of fuel which goes here. And you have oxidizer which goes here. That's classical scenario that you may happen in rockets, when you have any kind of nozzle, any kind of propulsion. So, this is generally speaking, what will happen is diffusion kind of flame. Okay? So, diffusion flame. I'll just show very basic. We have about 10 minutes, so I will show basic introduction. This is kind of diffusion flame. So, typically, bulk flame, most combustion happens here in a diffusion mode, isn't it? But here, what we may have, we also have mixing. So fuel is mixed with oxidizer here and here. So this mixing actually provides some kind of premixture. And actually, in addition to this diffusion bulk flame, you will have two premixed modes here, and the same here. Sometimes it will be a whole premixed mode, or sometimes it will be like whole premix. It will be just partially when something will be here and something will not be. So here is the general picture. And that is a flame. Sometimes it can be like attached flame to the nozzle. Sometimes it can be lifted up. And so what is important to realize? That yes, in terms of energy release, this is typically what we call diffusion. What we call typically is diffusion flame. But this is what we call base here. And this base, it provides you premixed flame mode. So these are premix segment. Left lean premix segment in the left hand side, right hand side, and rich premix segment. And if you see picture here, what is more important to realize here? That this is not, when we talk about typical classical flame, we say, okay, that it can be lean, it can be rich. And depending on substance, depending on equivalence ratio, you have what? You have planar flame speed. Now, here, it will be really something fully different. So here is my big flame, and here I have two segments. So basically, here there will be so-called triple point or stagnation point when these segments intersect. So here, let's see. So here on the left-hand side, what will happen? I have oxidizer, okay? Here I have fuel, so they mix somewhere here. So what kind of I have here? What kind of flame do I have here? If I have abundance of oxidizer. How we call a flame but with more oxidizer than fuel? It's lean, fuel lean flame. So here's lean segment. And the more I glow towards the fuel, here it will be more rich, right? Here in contrast, I have just fuel with a little bit abundance of oxidizer. So here is rich flame. And when they intersect, it will be some point when we have stoichiometric condition. And this stoichiometric condition, when they have intersection with this bulk line. And why it's important? Because stability of this big bulk diffusion flame will be given by premixed mode. Because it is premixed mode which oscillates and then it will kill it. And that's something that will be responsible for screening. Here it is. So that's what is important to remember. Now, what is also important to remember that this flame, it does not have constant velocity. It's big scenario, and each local point here corresponds to different equivalence ratio. So that is certain equivalence ratio, and here your flame becomes nothing but a function of space. So basically here it's one SL, here it's another SL, another SL, another SL. And Please realize this flame. Remember we talked about Bunsen burner, and your problem in your homework number 4 before, it was a question about Bunsen burner. When your Bunsen burner was compensated by the flow. And we say that your planar flame speed cannot exceed flow velocity. The same story here. You have flow velocity, so when you generate a flame, your flame is generated in such a manner here, in such a manner that it's balanced by the velocity. So it is your nozzle velocity which will generate a flame. So here is your flow velocity, and you will get the following, that at stabilization point, your flame and the mixture fraction becomes function of the inflow velocity. That is really nice to realize. And we have steady conditions. So basically that it is. So that is my structure. And if I want to describe this picture, this flame, we will see the following, that your planar velocity now is nothing but a function of flame and flow parameter. It will be function of radius of this channel. It will be also, it will be function of position. It will be function of diameter of this channel. And there is classical theory by Chung that only if Schmidt number, remember we have Lewis number, it's ratio of Prandtl to Schmidt number. So when Schmidt number is in this interval, you may have stable or unstable solution. So what you were able to do, there are different, I want to recall a little bit. So there are different components how we can consider instability interaction with combustion. There is Rayleigh-Taylor instability, Kelvin-Helmholtz, real and Dow, diffusional, thermal, and parametric, we discussed. And remember, we described how we consider the instability. If you consider flame propagation by the front, you may consider the linear solution and impose the acoustics, remember? And I believe you saw these pictures when we talk about flame acoustic coupling. It was chapter 8. Now we are able to employ exactly the same strategy here, exactly the same. But key point here will be the following, that now your scaling, your planar flame speed will be function of space. And if you describe your stability here, you will describe the stability of the entire fluid. That's why almost the entire course we deal with premix flame. Even in fire safety, in forest fires, you will have diffusion flame, because this segment really it's premix based combustion. Okay, I think I was very small part of the lecture, but I wanted to spend these 10 minutes to introduce you in triple flames. I believe maybe I can record this lecture in a more sophisticated manner, briefly, very briefly. And maybe I can also talk about this a little bit on Thursday, but also on Thursday, I want to deposit more and more time on maybe question and answers, or also lecture 15, which will be related to extension of combustion science. Okay, what I'm going to do right away when we end up the lecture, I will send you homework number 6. It's like a take-home quiz, and I do ask you by tomorrow, please send it back to me, such that I can post my solution and we can discuss it on Thursday. Okay, it will be promptly to do it. I believe you can do it really tonight in 20 minutes or whatever, because really I made it in such a manner that you don't need to solve the problems. But this really some good quiz in terms of preparation to your final exam, because just in a week you will have your final exam, right? Okay, please, any questions? Please ask me something. Ask me. Everybody understood everything? Really? Okay. Anyway, you know how to find me. If you have any questions, please contact me, and I will post this video tonight. It will be there so you can follow it. And also right now, I will send you this home task. So please do it. Please do it. Okay. Then again, let me